So mass action law is another aspect where before I start mass action law, just want to post you in a semiconductor at any given temperature. All the time, two things will simultaneously happen. What are they? One, electron hole pair generation. The other, electron hole pair recombination. At a given temperature, how many generations happen? The same number of recombinations happen. Why? If this is not true, either the concentration keeps decreasing or the concentration keeps increasing. But such a situation is not happening. You say that at a given temperature, this is the number of free electrons, this is the number of holes. Likewise, you are telling. When is this possible? When that equilibrium is possible. So mass action law speaks about the same. So under thermal equilibrium, okay, the hole concentration into electron concentration is Ni square. Ne refers to free electron concentration, not electron, free electron concentration. NH refers to hole concentration. And then what is Ni? Intrinsic carrier concentration. In a pure intrinsic conductor, Ni is nothing but either Ne or NH. Intrinsic carrier concentration. So I repeat, what mass action law refers to us is when thermal equilibrium exists, the product of concentration of free electrons and concentration of holes is a constant, and it is equal to intrinsic carrier concentration. And this law is a mass action law. And remember, this is again independent of amount of donor and acceptor doping level. That is mass action law. Again, charge is also conserved. That is also another law. The entire numericals you will do on the basis of this. అవును. ఇంట్రెన్సిక్ లో అదే కరెక్ట్. ఇంట్రెన్సిక్ సెమీకండక్టర్ లో Ne is equal to NH is equal to Ni. బట్ పీ టైప్ లో కానీ ఎన్ టైప్ లో కానీ Ne is not equal to NH. రైట్. ఇప్పుడు లా ఆఫ్ కన్జర్వేషన్ ఆఫ్ చార్జ్ బేస్డ్గా ఒక ఎనదర్ అబ్జర్వేషన్. This is again, we are classifying this into two categories. The first part is The other part is P-type semiconductor. See, you should follow very, very, very carefully this part. The problem is, I noticed that the first video was not studied by all of you. That is the reason why you are responding a fresh look to some of the terms which I am introducing here. Let us define ND refers to concentration. Can I ask you one question? What is the meaning of concentration? Number per unit volume. Concentration of donor atoms. Concentration of donor atoms in intrinsic semiconductor. At room temperature, I'm speaking about room temperature. Almost every donor atoms donates one electron. That is why it is called a donor. And therefore, concentration of free electrons due to donor atoms is ND. This is same as concentration of free electron, not total free electrons, remember. Due to donor atoms. Right. Right. No, mostly to avoid confusion, we will write Ne almost end. And this is an N-type material. Much, much greater than NH. So, mass action law in this case is Ne times NH is equal to Ni square. This is universal. Whereas for N-type material, N donor into NH is Ni square. So therefore, in an N-type semiconductor, if you want holes concentration, simply use this relation. Otherwise, you are supposed to use number of positive charge the same as a number of negative charge. మీరు ఏమని రాస్తుండేవాళ్ళు అంటే నెంబర్ ఆఫ్ ఎలక్ట్రాన్స్ నార్మల్లీ నెంబర్ ఆఫ్ ఎలక్ట్రాన్స్ is equal to number of holes plus number of donor atoms. Likewise, I would have written. But in this case, I am not going to write like that. I'm straight away writing like this. This is N-type semiconductor. So this part is done. So now I'm moving on to other side. Moving on to the other side. The other side is P-type semiconductor. When you said donor in N-type material, what is the contrary word for P-type material? Acceptor. Correct. So if Na refers to concentration of acceptor atoms, and again you know the working style of P-type material, each one accepts only one. So therefore, what will happen in that case is number of holes is indirectly Na. Right. So though what is happening here in p-type semiconductor is that n holes much greater than n electrons. So therefore, mass action law in this case refers to mass action law in this case refers to Ne, Nh is Ni square, Ne, N acceptor is Ni square. So therefore, if you ask me, Ne in this case, it is nothing but Ni square by Na. Earlier days on PN junction, before PN junction, not on PN junction. Before PN junction, if there is any question related to the construction of N-type material, P-type material, they used to ask these areas under numerical category. So straight away, I am now picking up the next part of the discussion. Already, you know, mobility term, you know, in a mobility is defined as drift velocity by electric field, unit electric field. So therefore, mobility is V drift velocity by E. You already know mobility of electron is much greater than mobility of holes. For example, not much greater than or greater than at least. For example, I'll just give you some comparison. So basically, we deal with the germanium and silicon. In a germanium material, the mobility of electron is of the order of 3,800. Remember, the units are interesting. Drift velocity per unit electric field. Don't forget that. What is drift velocity? Centimeter per second. Electric field, volt per meter. Electric field, W volt per meter, volt per centimeter otherwise. So it is like volt centimeter square by volt second otherwise. Whereas on the other hand, silicon, it is 1300. Whereas if you expect the same thing in holes, see, holes is exactly half of this nearly. Nearly half of this. Only for some idea I have given this. So always mobility of conduction electrons, mobility of conduction electrons. Can you please tell me what do you mean by conduction of electrons? These are the electrons which are freely moving in conduction band. Is more than mobility of valency electrons, valency band electrons otherwise. Right. Right. Next, mobility depends on temperature. In fact, mobility is proportional to T to the power of -3/2. Okay, right. Next, we all know conductivity from electrostatics. Conductivity in electrostatics, we will represent this with sigma, rho for resistivity. And it is nothing but Ne square tau by M. right? N E square tau by M. You already know this. Okay, for an intrinsic semiconductor, intrinsic semiconductor. By the way, you already know one more important term, Ne mu. In current electricity, you know. In current electricity, you know this. You may ask me, how do you know this? E is rho J. Do you remember? Sigma is J by E. J means, uh, you know, current current density, N E VD by E. VD by E is mobility. So therefore, sigma is N E mu. This is all in current electricity. We are learning all these things in current electricity only. So no need to work fresh. So N holes, E holes, mu holes plus N electrons, E, because charge of the electron itself is E. Even for EH also E, mu E. Okay. Mu అంటే మొబిలిటీ. అది ఆ మ్యూ వేరు, ఈ మ్యూ వేరు. ఆ మ్యూ రిఫ్రాక్టివ్ ఇండెక్స్, ఈ మ్యూ మొబిలిటీ. Mobility, drift velocity by electric field. Nowhere linked with either dielectric or anything else. Right. Asal, first of all, how are they linked? Tell me. Right. Electric field, మామూలుగా కండక్టర్లో ఉంటుంది కదా, which is responsible for the drift. అదే ఉంటుంది, ఇక్కడ కూడా ఉంటుంది. అందుకే మొబిలిటీ డిస్కస్ చేస్తాం. అదే మీరు సేమ్ సిచ్యువేషన్ పీ టైప్ మెటీరియల్లో డిస్కస్ చేయాలనుకోండి. ఫర్ ఎగ్జాంపుల్, ఫస్ట్ ఎన్ టైప్ మెటీరియల్ చూడండి. ఎన్ టైప్, పీ టైప్ కన్వీనియన్స్కే మనం మాట్లాడుకునేది. అది ఏం నెగిటివ్ పాజిటివ్ కాదు. ఈవెన్ ఎన్ టైప్ అయినా నెట్ న్యూట్రలే, పీ టైప్ అయినా నెట్ న్యూట్రలే. ఎన్ టైప్ వచ్చేసేటప్పటికి మీకు అసలు హోల్స్ రోల్ ఏమి ఉండదు ఇక్కడ. సో అంతా ఎలక్ట్రాన్సే ఉంటుంది. సో ఎలక్ట్రాన్స్ ప్లేస్లో డోనార్, ఈ కూడా రాసేయచ్చు. ఎలక్ట్రాన్స్ ప్లేస్లో డోనార్, ఈ మ్యూ ఎలక్ట్రాన్స్. ఇదే పీ టైప్ మెటీరియల్కి వచ్చారనుకోండి మీరు, ఇదే సిగ్మా ఎన్ యాక్సెప్టార్, ఈ మ్యూ హోల్. ఓకే, రైట్. See, I will take numericals a later stage. ఎప్పుడు మీ వాళ్ళకే తక్కువ కాదు. దట్ ఈస్ నాట్ ద రీజన్ యాక్చువల్. అది కాదు రీజన్. దట్ ఈస్ నాట్ ద రీజన్. అంటే ఎలక్ట్రాన్ ఫ్రీ అవటం, యూ విల్ గెట్ ఎ ఫ్రీ ఎలక్ట్రాన్. ఎక్కడో ఫ్రీ అయిన ఎలక్ట్రాన్ దగ్గర మళ్ళీ బాండ్ ఫార్మ్ అవటం హోల్ పార్ట్. అర్థమవుతుందా? రైట్. నౌ వీ విల్ మూవ్ ఆన్ టు పిఎన్ జంక్షన్. Till now, you have studied independently P type separately, N type separately. Now we are studying the P and N type together in one shot. For this purpose, for this purpose, I require a small diagram. Now see, same time in an intrinsic semiconductor, one side we will diffuse uh, p-type impurity, the other side we will induce, we will diffuse n-type impurity, so that during the crystallization itself, this border forms. What exactly happens in a p-n junction? Let us work on this. What exactly happens? Every semiconductor device which we are using in the name of a diode, transistor, etc. This is the basic element, the first semiconductor element, otherwise I can say, which you need to understand. Tomorrow you may design anything else using semiconductor devices. This is the basic building block. What is actually happening in case of a p-n junction during the formation itself? We already know in this particular case, in p-type, holes are more when compared to A. So hole concentration is more when compared to electrons. In n-type material, electron concentration is high when compared to holes. So across the border, what is actually happening across the border? You see, across the border, what is exactly happening is, you will notice diffusion of holes from P region to N region. Across the border, left side holes are high, right side holes are less, because right side is an n-type material. So diffusion of holes takes place from P to n-type. Similarly, electrons are high. Concentration of electrons is high in n-type when compared to p-type. So across the border, right side electron density is high when compared to electrons in the p-type material. Hole diffusion is from P to N. Electron diffusion is from N to P. Now, what happens because of this? Analyze. Now, what happens? This will deal two things. One is in this direction, you will have hole diffusion. Okay. In this direction, you will have electron diffusion. Effectively, in this direction, you will have diffusion current. No, tell me, have you accepted this or not? Just because of this, what will happen is that In the formation itself, what you can notice here is, see these holes drifted to, actually this hole diffused to that side, and that electrons diffuse to this side. This will create a region of space of immobile charges, and that is called depletion region. Now, what is happening? Previously, please note that what is the status of this? This is hole, and here you have an electron here. Now, remember, in the absence of the filling of the hole, it is neutral. The moment it accepts, what happens to that? It becomes a negative. I am not confusing you. Forget about the right hand side. Let us speak only about this. What do you mean by hole? A deficiency of an electron. That doesn't mean it is already lost. It's deficiency of electron. That deficiency is filled by an electron. Now that particular atom will have excess of one electron. So it is negatively charged. Similarly, electrons this side are in neutrality only. The moment they lose, they will become positively charged. Now, across the border, what is happening for you? Across the border, an immobile positive charge, an immobile negative charge will happen. And this happens only across the border. Now, what happens is this will set an electric field in this direction. When this is setting an electric field in this direction, this electric field will drift electrons from P region to N region. Don't get confused. Previously, what happened? Previously, diffusion happened from P region to N region. Diffusion of holes happened from P region to N region. Now, what is happening? This electric field favors the motion of electrons from P region to N region, and that is called drifting. On the other hand, the same field encourages drifting of holes from N region to P region. What was happened earlier? Electrons moved from N region to P region. Now, what is moving because of this electric field? Holes are drifted from N region to P region. Please avoid confusion here. Yes, they are different. They are happening due to minority charge carriers. And diffusion current is due to majority charge carriers. No, you speak of net, man. Not only holes. Diffusion, major charge carriers. Drifting is due to minor charge carriers. For example, when I said holes from N region to P region means N region they are minorities and P region they are majorities. తక్కువ ఉంటుంది. Right. So diffusion current is from P region to N region and drift current is from N region to P region. So after some time, some equilibrium take place where there is some enhancement of the region of depletion part, and this avoids net zero current. This is responsible for net zero current, and this space charge region is actually a depletion region or space charge region. Both represents the same situation. Depletion region or space charge region. Now, whatever that you notice here, they are completely immobile. Now, the entire thing we will represent as a symbol like this. This region stands for P-type and that region stands for N-type. Now, across the border, you can notice a potential gradient is established. This is the border. Across this, a potential gradient is established. So that which overcomes this will join P region to a hole which need to cross this region to reach here require some external biasing. By itself, it cannot cross now. ఇది హోల్స్కి మనం గీసేది. ఎలక్ట్రాన్ కూడా ఇట్టనే ఉంటుంది, ఆపోజిట్ సెన్స్. ఇది ఎలక్ట్రాన్కి ఏమవుతుంది? ఎలక్ట్రాన్ దిస్ సైడ్, electron has a tendency to move from, general tendency to move from high potential to low potential. Okay. Holes will move from high potential to low potential. Electron will have a tendency to move from low potential to high potential. I should correct myself. Previously, I uttered wrong. Electron will have a tendency by naturally to move from low to high. Holes will have a tendency to move from high to low. Now you are giving a reverse situation here. For a hole, this side to this side refers to what? Low to high. By itself, it cannot go. Electron naturally moves from low to high, but all electrons are this side. So they themselves cannot move from a region of high potential to low potential. This is called barrier potential. So how you will overcome this? By proper biasing, and that we will call as PN junction in forward biased mode. In this case, what is happening? This PN junction, which I have demonstrated symbolically like this, we will connect this to a battery such that the P positive side of the battery is the P side and the negative side of the battery is on to the N side. Forward bias, now the holes will be pushed towards N side by this battery. Similarly, the electrons of N side are pushed towards the hole by the battery. Now this charge ఉంటుందిగా, కొంత అస్సలంటూ ఉండకుండా ఉండదు, కొంత ఉంటుంది. ప్యారలల్ ఎందుకు పెట్టాలి చెప్పు కదా. నేననేది the purpose of this is to control the drop across this point. Why we do this is to control the potential drop across the diode. Any doubts? Now, if you plot a graph taking voltage along x-axis, forward current along y-axis, you will notice that the graph behaves like this. Till certain point, it behaves like a straight line. Thereafter, exponentially increases. Remember, till this point, there is no current. Why? Because this should cross that barrier voltage. Once that barrier voltage is crossed, the holes starts again diffusing to n region. Electrons will start diffusing towards hole region. And in this case, even though there is a drift, it is negligibly small. Very, 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 very small. So this is how the characteristic. Remember the voltage is of the order of some uh, 0.5 volts in case of germanium and 0.7 volts in case of silicon. Approx, just giving a rough idea. The same PN junction diode if used in reverse biased mode. In this case, ideally there won't be any current. And thereafter, there will be current, and this current is independent of the voltage thereafter. And this is called this breaking voltage. So, I mean, whatever you give, nothing happens to thereafter. And this region is called breakdown region. And this is breakdown voltage. Breakdown voltage. This region is breakdown region. ఒరే మీరు ఏం వింటలేదురా నాకు అప్పుడు సైలెంట్గా చెప్తున్నారు చూస్తున్నా వినరురా మీ పిల్లలు అందుకే ఇదంతా నేను చేయను. Why there is a breakdown region? That's the first question. నువ్వేమి అప్లై చేయలే, యూ కెనాట్ అప్లై ఎనీ ఫర్దర్ వోల్టేజ్ ఆర్ యూ విల్ నాట్ నోటీస్ ఎనీ డ్రాప్ అక్రాస్ ద డయోడ్ దేర్ ఆఫ్టర్. Current keeps on increasing. What is the reason? What is the reason for a breakdown, first of all? See, in this case, what will happen? Yes, you are increasing the voltage, the width of the depletion region increases. Remember, under forward biased condition, the width of the depletion region decreases. Under reverse biased condition, width of the depletion region increases. So the strength of the depletion region is so high. Electric field across the border is so high that all of a sudden it will break the covalent bond on either side. Then what happens? All of a sudden you will have electron hole pair creation. So then what happens? Electrons, because of that drifting, remember normally what is expected in a forward bias condition, electrons need to move from n region to p region, holes need to move from p region to n region. Normally, forward bias condition. In reversed bias, drift current dominates. So electrons from n region move to p region, holes from p region moves to n region, and this motion will ignite a series of collision. An electron which is fastly moving across n to p region will hit one more electron in the bond, and that creates additional electron hole, and this is like an avalanche. You know, in snow mountains, you will see avalanche. The drift current is the dominating factor. Diffusion is literally zero here. No diffusion current in reverse bias. Forward bias mode, even though there is a small drift, negligible. Drift current is of the order of 10 power minus 6 amps, whereas the diffusion current is of the order of milliamps, 1,000 times more. Even you will not notice at all. You will not notice at all. But here there is zero diffusion current. The only current which is possible is drift current. Any doubts? Ah, see here you have a stock of holes. Here you have a stock of electrons. The problem is the natural tendency of electrons. The natural tendency of the electrons is to move from this side to that side, this level to that level. See, low, high. This is the natural tendency of the electrons. The natural tendency of hole is like this. But the condition available to you is reverse. N side, which is higher side, you have electrons. P side, which is lower side, you have holes. So this will stop diffusion current. You require some biasing externally to maintain a current flow. So therefore, in forward bias, you are supporting that. In reverse bias, even though that is due to drift current, but at some point called breakdown region, breakdown voltage, even you add externally, nothing happens across the diode. It simply maintains that constant voltage, and rather the current keeps increasing. Reverse bias, the depletion region will thickness will increase. Forward bias lo depletion region decrease అవుతుంది. Don't forget they are immobile charges. So nothing happens to that. Inka more electron, more holes pair creates, and that will leads to more extension of the depletion region. Okay, we'll just stop over here.